That's the deal with polynomials, is they're always smooth. So I'm going to show you examples of everything on Desmos really quick. Like if you have the curve y equals 1 over x. This curve, is it continuous? No. Because if you were going to draw that with your pencil, you have to, at some point, pick up your pencil if you want to continue drawing the curve. And that point right there at x equals 0 is what we call a discontinuity. What about the next function, the absolute value of x minus 2 plus 1? Try that again. Y equals absolute value of x minus 2 plus 1. There we go. Is this continuous? Yeah. You can draw the whole thing. What about smooth? Is this smooth? No. So you can tell where the one part of that curve is that's not smooth. And so this, if I showed you a picture of this on an exam, you'd say that definitely cannot be a polynomial because it's not smooth. And polynomials have to be smooth. What about x to the 2/3 power? Is that continuous? Yeah, you can draw the whole thing. What about, is it smooth? Nope. So it could not be a polynomial. If you saw a picture of that, like I might give you a picture on a test, you would say that cannot be a polynomial. And again, if I were to plot any old polynomial, you would be able to tell that the polynomial is smooth. And that is something to know. Also, if you have any old continuous function, and you're looking at the curve, and as you read from left to right, the curve is going up, then we say it's increasing. That should be pretty easy to remember. Increasing means you go up from left to right. Decreasing means the curve goes down from left to right. So let me come up with a little function that we can talk about. If I have the function x cubed minus x, maybe. This is a function where on the left side, this is increasing. It's going up as I go from left to right. And it continues to increase until we reach the point where x equals negative 5.8-ish. Sorry, negative 0.58. And then it starts to decrease, right? It switches from increasing to decreasing. And it continues decreasing until you get to the point x equals positive 0.58. And then after that point, it starts to increase again. Okay? Every place where your function switches from increasing to decreasing is going to be called a local maximum. So we've got a function that's increasing, and then it switches from increasing to decreasing. This place must be a local maximum. And we call that a local maximum because there might be another spot in the function that has an even greater value over here. But at least if I look in its local neighborhood, just the set of points there, just next to it, that is the maximum. Likewise, if a function is switching from decreasing to increasing, like right here, my function's decreasing and then it switches and it starts to increase. This would be a local minimum. And it might be the case that your function has other places with an even smaller value, so it's not the absolute minimum. Got smaller values over here, but at least within its little neighborhood it has the smallest value, so we call it a local minimum. Anytime you have a local maximum or a local minimum, you might also call it a turning point because it's a place where it turns from increasing to decreasing. For a minimum, it turns from being decreasing to increasing. So a turning point is an umbrella term for maximums and minimums. And the degree of a polynomial is going to determine the maximum number of turning points, and it's going to determine whether the number of turning points should be even or odd. When I say the number of turning points and the degree are numbers with opposite parity, then what I mean is that if the number of turning points, or I should say, maybe if I should say, the degree is odd, an odd degree implies an even number of turns. And since this is opposite parity, if the degree is even, that would imply your curve is going to have an odd number of turns. And then the other thing is that the number of turning points is always less than the degree. So, in this first example, right here, my degree is 7, right? This is an expanded form, and when it's an expanded form, the degree is the largest power of x. So the number of turns could be, well, it has to be an even number, and it has to be less than 7. So it could be 6, or 4, or 2. And if it's even, we also say 0 is a possibility. So include 0 on the list. What about this one? The degree is 4. And so the number of turns could be 3 or 1. It has to be an odd number, and it has to be less than 4. So I forgot to include this on your homework, but one possible exercise is, could you make a degree 7 polynomial that has 6 terms? It's not that easy. You might start off with x to the 7th power, and then to get 6 turns, I mean, if I just try to guess at something, I've only got 2 turns so far. To make this more turny, I might try to increase some of these coefficients. Oh, there we go. That wasn't so bad. Okay, so how many turns? 1, 2, 3, 4, 5, 6, right? Every local maximum or local minimum, a place where it goes from increasing to decreasing, or from decreasing to increasing, that's what we call a turning point. You can see I got 6 of those. But something to try on Desmos, if you have a moment to spare. And then, the most basic, easiest maybe to remember way of graphing a polynomial would be to start by generating a table of values. This isn't the most elegant way to do things. We're going to talk about better ways to do it, but if you are taking your test and you completely blank and you cannot remember the more sophisticated way of graphing a polynomial, one brute force method of doing things could be generating a table of values. So if I want to graph this, I would start with saying x equals 0. If x equals 0, then y would be -3. Very good. And then what about if x is equal to 1? That would be 1 plus 3 minus 1 minus 3. So y is 0. What about if x is equal to 2? Then this is 2 cubed plus 3 times 4 minus 2 minus 3.
I think one is 1 if x 1 is never 1.
Okay. Yeah, right now I'm mentally trying to double check my work because I do make mistakes a lot. So Feel free to double check me. If x is equal to 3, then y would be equal to 3 cubed plus 3 cubed again, minus 3 minus 3. Well, this is going to be off the scale, right? This is going to be a big number. In fact, I made a mistake already and nobody corrected me. But if x is equal to 2, y is really equal to 15, I think, right there. Right, I think I messed up like a positive or negative sign, because this should have been 8 plus 12 minus 2 minus 3, so it should have been 15. This is what I mean by I make mistakes a lot, so try to pay attention enough to correct me if I make a mistake. And once you get to this point where like you plug in an x value and you get a y value that's larger than 10, you can stop, because if it's larger than 10, it's already off the graph and you can't graph it anyways, right? So I could have stopped at x equals 2 because 15 is larger than 10, and that's going to be off the scale. Then we go in the opposite direction, and I say, okay, what if x is equal to negative 1? If x is negative 1, then this would be negative 1 plus 3 plus 1 minus 3, so y is 0. Next, we would try x equals negative 2. We get negative 8 plus 12 plus 2 minus 3. And then y is 3. What about when x is equal to negative 3? Get negative 27 plus 27 plus 3 minus 3. 0. What about when x is equal to negative 4? You start off with negative 64 and then plus whatever. This is a really big negative number. And so it's going to be off the scale again. It's going to be a negative number larger than negative 10, so I'm not going to be able to graph it. And I can stop. But now I would go back and I would place all these points. So when x is equal to 0, y is equal to negative 3. When x is equal to 1, y is equal to 0. When x is equal to 2, y is 15. So it's like way up here off the scale. And I can't really put that point down. But I know it's going up to reach that point, so I can draw something like that. When x is equal to negative 1, y is 0. When x is equal to negative 2, y is equal to 3. When x is equal to negative 3, y is 0. And then again, when x is equal to negative 4, y becomes this really big negative number. So it goes down off the scale like that. And then I would just connect my dots. And using this kind of brute force method, that's my best guess at what the graph should look like. Any questions about how we did that? No? Okay. Like I said, we'll come up with a better way of graphing polynomials at the end of class today. Something that's faster and more accurate in a lot of situations. But if you happen to forget things, then this is what you could do on a test to rule out possibilities. This exercise says complete a table of values by looking at the polynomial curve. And that means make a table of x and y values. As I come in from the left, I notice x equals negative 4. Well, I don't know what that y value is because it goes off the scale, but x equals negative 3 looks like it corresponds to this point, and y is 6. When x is equal to negative 2, y is 0. When x is equal to negative 1, y is negative 1. When x is 0, y is 0. When x is 1, y is 0. When x is 2, it looks like y is going to be -4. And then if x is 3, oh, it's 2 negative, right? So that's it. That's all you have to do. Plot the points that appear on the graph. The way you might extend this problem on like a homework or a test is you might say, now let's go ahead and write the polynomial function that generated that curve you see. And even though this question is asking me to put the function in expanded form, we're still going to start with the factored form. And I'm not going to make this a trick question, so don't overthink it too much. What I can tell from this graph is that I have how many roots? I've got 3 roots that are visible on the graph, because every time I have a 0 of my function, I have a root of my polynomial, and the zeros of the functions are also the x-intercepts. And I see 3 x-intercepts on this curve, so I've got 3 roots of my polynomial. So my roots are going to be at -2 and 0 and +1. No, the zeros are not turning points. You'll notice there's 2 turning points on my graph. I've got 1 turning point that's a local minimum, and 1 turning point that's a local maximum, but they actually have 3 zeros, or 3 roots, and those are different points. Those are not the turning points. And if I want to write my factored form, it would look like a leading coefficient times x minus one of the roots times x minus another root times x minus the third root. And normally in factored form, we would also allow the possibility of having other multiplicities, like having these factors raised to the 1 power or the 2 power or the 3 power and so on. But again, I'm usually not trying to trick you, so don't overthink it too much. If there are 2 turning points like this, what's the smallest degree polynomial that could allow you to have 2 turning points? The degree of a polynomial has to be larger than the number of turning points. Okay? The degree of your polynomial has to be greater than the number of turning points. So if I've got 2 turning points, my degree has to be at least 3, right? It could be 3 or 5 or 7, because the degree has to be odd if I have an even number of turning points. And if I have 2 turning points, I have an odd degree, and it has to be larger than 2. 3 is the smallest degree possible for this graph. If I've got 2 turns, then the smallest possible degree is degree 3. We also know that if my polynomial is given in factored form, then the degree is what I would get if I add up the multiplicities. Right? Let me remind you really quick about the degree. If it's in expanded form, then the degree is the largest power of x in expanded form. But if your polynomial is in factored form, you can tell what the degree is by adding up the multiplicities. And if I want my degree to just be 3, then the only possibility for these multiplicities is that all of these multiplicities are 1 plus 1 plus 1. And like I said, don't overthink it too much. In this case, the multiplicities are just 1 and I won't try to trick you in any way. And like I said, I know what these roots are because we can tell what the x-intercepts are. The roots are -2, 0, and 1. So let me fill that in. For my roots at -2, 0, and 1. And x minus 0 is just x. I almost have this in factored form, except I don't know what my leading coefficient is. And we can find that leading coefficient by choosing any other point, as long as it's not a root. Let's just go back to this table that I put together and say, let me pick one of the points. In fact, let me pick the point x equals 2, y equals -4. You could have picked any of the other points. You could have picked -1, -1, or -3, 6. But again, we have to choose one. So let's move ahead with x equals 2, y equals -4. And then I'm going to get -4 equals a times 2 times 2 plus 2 times 2 minus 1. And that means -4 is equal to a times 8. And if I divide both sides by 8, a is equal to -4 over 8. And that fraction simplifies to -1/2. And since I know a is -1/2, I could come back here and plug in -1/2, and this is in factored form. My question asked me to put this in expanded form, right? We said, write the polynomial function in expanded form. That generated the curve. Well, now I've written the function in factored form that generated the curve. I'm almost there. I just need to expand. And we've done this before. In the lecture number 3.1, we have expanded. What I might want to do first is multiply the last two factors together to get x squared plus x minus 2. And then I have to distribute -1/2 x. Now I get -1/2 x cubed minus 1/2 x squared plus 2x. No. Plus x. Because the 2 and the half cancel, two negatives make a positive, and then this would be my answer. Do you guys have any questions about how we wrote that down? No questions? If you wanted to check your work, how could you check your work? Right? If you're taking a test, you want to make sure you didn't miss any points on your test. I could check my work just by picking one of these points that I haven't already used. And maybe I want to plug in x equals -1 down here. Replace the x's with a -1. Evaluate that. And if I get y equals -1, that would be a really solid confirmation that I wrote the right function. But if you plug in x equals -1 and you simplify and you get y equals 5, then that means you did something wrong and you've got to go back and find your mistakes so you don't lose points. But you can check your work by just choosing any other point that you haven't used, plug it into the function you got at the end, and make sure that it works. So like I said, today we're going to just do only problems where we graph polynomials or look at graphs. The most important things to get right are the roots of the polynomial and their multiplicities, the y-intercept, and the end behavior. And you know, on a graph, the roots of the polynomial become x-intercepts. The y-intercept is whatever you get if you plug in x equals 0 into your function. And when I say end behavior, what I mean is, if you're looking at a graph, there may be a whole bunch of action happening in the middle here, but the end behavior is what is happening if I go far enough to the right. Is it going up or going down? And what happens if I go far enough to the left? Is your function ultimately going up or down if you move far enough one way or the other? And end behavior depends on the degree of the polynomial, and it depends on the leading coefficient. I care about whether the degree is an even number or an odd number, and I care about whether the leading coefficient is positive or negative. Okay, if the degree is even and the leading coefficient is positive, the end behavior is up on the left and up on the right. If the degree is odd and the leading coefficient is positive, it's going to be up on the right, but down on the left. If the degree is even and the leading coefficient is negative, it's down on the left, down on the right. And if the degree is odd and the leading coefficient is negative, it's going to be up on the left, down on the right. This whole thing is technically something you are expected to have memorized for the next test, test number 3, and for the final exam. But I'll give you a trick to memorize this. And my trick here for memorizing this table is, first of all, you have to remember that degree and leading coefficient matter, and nothing else matters. But I care about even degree, odd degree, positive leading coefficient, negative leading coefficient. Hopefully you can remember that. And if you do remember this, the way you fill in the table, or the way I think about it, you know, I don't have this memorized literally, but what I think about is I think, what is the simplest function that has an even degree and a positive leading coefficient? Y equals x squared has an even degree and a leading coefficient of positive 1. And I remember that the graph of y equals x squared looks like this. We've graphed parabolas before. We said if the leading coefficient is positive, then your parabola is up on the left, up on the right. And then the other thing you would want to remember is, what is the simplest function that has an odd degree and a positive leading coefficient? Y equals x. And y equals x is a line. We've graphed lines before, and so you know this has a slope of positive 1, so it's going up, it's increasing. And that line must be down on the left and up on the right, and so that's how you fill in the end behavior for that part of the square. And if you can remember that, you got the top half, up, up, down, up. The way you can remember the bottom half of this table is to think, well, if my leading coefficient is negative, I just take the opposite of every single arrow. So instead of up, up, it becomes down, down, up, down. Maybe those memorization tricks will help you out so that this table isn't so hard to remember. But again, that is something you got to know. I'm going to continue now by assuming that everybody knows that. And we'll show lots of examples today of how we're going to use that knowledge. But moving on, the x-intercepts of a polynomial curve are also the roots of the polynomial. And let's talk about multiplicity. If a root has even multiplicity, we're going to say that the curve is going to bounce. Maybe that doesn't mean anything right now, but I'll tell you what that means here in a moment. If the root has odd multiplicity, that means your curve is going to cross. Since the roots are places where we have our curve touch the x-axis, if that root has odd multiplicity, when it touches the x-axis, it's also going to cross the x-axis. And what I mean by bounce is it's going to look like the curve does not cross the x-axis. Let's look at a picture. I'm going to give you a polynomial here that is in factored form. And in this polynomial, the first root you see is positive 1. And so right here at x equals positive 1, I have an x-intercept. And since the multiplicity of this root is 2, 2 is an even number. An even multiplicity means this is going to touch the x-axis, but it's going to bounce off of the x-axis. That's what I mean. Do you guys remember root multiplicity? I'm saying that the multiplicity is 2 because of the exponent 2 right there. Okay? The other root happens at x equals negative 3. And at x equals negative 3, I've got an x-intercept where this curve crosses the axis. And the curve crosses the axis because the multiplicity is 1. And 1 is an odd number. Anytime you get an odd number multiplicity, the curve is going to go through the x-axis like it does right there. So when I use the words cross the x-axis, it looks like that. When I say it bounces off of the x-axis, it looks like the root at positive 1 there. And again, I love Desmos. I'm glad I'm not teaching math 30 years ago when you didn't have Desmos. But you can see, even if I choose a different odd number, like now this root here at x equals negative 3, this root has a multiplicity of 3 because of that exponent 3 there on the corresponding factor. But the curve still passes through the x-axis because the multiplicity is odd. And again, what if I had x minus 1 raised to the power 4? Well, that's still an even number, and since the multiplicity is even, it's still going to bounce off of the axis. So this is a critical piece of knowledge to have memorized. Do you guys have any questions about this? What we mean by multiplicity? Okay. So as we get ready to graph a polynomial, I want to get three things right. I want to get the x-intercepts and their multiplicities right. I want to get the y-intercept right, and I want to get the end behavior. If I get those three things, that's going to be good enough. So step number one, if I want to find the x-intercepts, I want to find the roots, and to find the roots, I want to factor this polynomial. If this were in factored form, I would be able to tell what the roots are. And so the first thing I would do is I would take out a greatest common factor. What's my greatest common factor? Yeah, it's just x, and then I'll be left with x squared minus 1. How do I factor x squared minus 1?
That's minus 1 x plus 1.
Very good. That factors as x minus 1 times x plus 1.
Reverse.
Yes, so we have three roots.
X equals 0, 1 negative.
Very good. And these roots have a multiplicity of they have a multiplicity of 1, 1, and 1. Because the factors that correspond to those roots, we say they have a multiplicity of 1 if they don't have any exponent written down, because x to the 1 power is the same as x. And if I say this parentheses is raised to the 1 power, it doesn't change anything, right? And if it doesn't change anything, then we typically don't write the little ones. But the fact that you haven't written anything means that the multiplicity is not 2, and it's not 3, and it's not 4, so it must be 1. That's why we say these roots have multiplicity 1. If you just don't see an exponent on the corresponding factor, the multiplicity is 1. All right. So that's step number 1. We found the roots and their multiplicities. Step number 2, we're going to find the y-intercept. And the y-intercept is what we get if we plug in x equals 0. If x is equal to 0, then y is equal to 0 cubed minus 0. Okay? And then last step, I want to know about the end behavior. And now you have memorized the end behavior table. And it cares about whether my degree is even or odd. And it cares about whether the leading coefficient is positive or negative. And the table is up, up, down, up, down, down, up, down. What about this one? Is my degree going to be even or odd? Yep. Degree is 3, and 3 is odd. What about the leading coefficient? That is positive 1, right? So positive leading coefficient, odd degree, means that my end behavior is going to be down on the left and up on the right. See how we did that? Okay. Now, we are completely ready to start graphing. And when I start graphing, I'm going to start off by plotting the x and y intercepts. Okay? I have an x-intercept at 0, 1, and -1. And the y-intercept is at y equals 0, and I've already actually plotted that dot, so I'm good. The next step is to say I'm going to draw arrows that indicate what the end behavior is. And on the left side, my end behavior is down on the left. So let's start from the dot farthest to the left, and I'm going to draw an arrow down on the left. Then we start to look at our right side end behavior. On the right side, I'm going up on the right. So I start at the dot farthest to the right, and I draw an arrow that goes up to the right. So now we've covered our intercepts and our end behaviors. The last step here is the hardest one. We are going to connect those 3 dots in a way that respects what the root multiplicities are. What I mean by that is, go back and look. Since these multiplicities are odd, it's going to cross the axis. And for this root, the multiplicity is odd, and so it's going to cross the axis. And for this root, once again, the multiplicity is odd, and so it's going to cross the axis. All 3 places, the curve is going to go through the axis. So it passes through, I connect the next dot and it passes through, and I connect the last dot and it passes through. This might not be very precise, but for our purposes, this is going to be good enough. I say this is good enough because I know I got the roots right, I know I got the multiplicities right, I know I got the y-intercept right, and I know I got the end behavior right. I don't care what else happens. This is going to give me the right shape of the graph, and all of the important points are plotted correctly. This takes a little bit more remembering. You know, at the beginning of class, we plotted a function just by making a table of values and then plotting the values and connecting the dots. That's what I would call like the brute force method. If you just want to be scrappy and you forgot everything you learned and you just want to get a function down, that's a way you can do it. This requires a little bit more process, thinking about it. But if you get good at practicing this, it's going to be faster. Okay, let's do another example. Graph the function. Step number 1. We want to find the roots, because the roots become my x-intercepts. And to find the roots, I would want to factor this polynomial. The first step in factoring would be to say, you know, do I have any greatest common factor? Yeah. I can take out a 3 and I can take out an x. And just because of personal preference, I'm going to go ahead and factor out negative 3x just because I like the leading coefficient to be positive. And after I factor out the greatest common factor, I get x squared plus 4x plus 4. How does that factor? It is a perfect square. So it would be x plus 2 times x plus 2. Or I could write x plus 2 squared. And so that tells me that my x-intercepts, aka my roots, occur at 0 and negative 2. And these roots have corresponding multiplicities of 1 and 2. Okay, so 1 is an even number, And that means at this point, my curve is going to... Sorry, did I say even? 1 is an odd number. 1 is an odd number. That means my curve is going to cross the x-axis. If 2, my multiplicity is 2. If 2 is an even number, that means my curve is going to not cross. Or you might say it's going to bounce. Okay, that's step number 1. Step number 2 says, let's think about my y-intercept. And the y-intercept is what I get if I set x equal to 0. And if x is equal to 0, y is equal to, yeah, it would be negative 3 times 0 cubed minus 12 times 0 squared minus 12 times 0. That means my y-intercept happens at y equals 0. That's not always the case. I know the last 2 examples have had y equals 0, but you will sometimes get different y-intercepts. And then the last part is I care about my end behavior. I know my degree is 3, and 3 is odd. I know my leading coefficient of this polynomial is negative 3, and I care about the negative part, right? So what's my end behavior look like? Remember, you're supposed to memorize this little table where I care about even, odd degree, positive, negative leading coefficient. You've got odd degree, negative leading coefficient, and you should know that this is up on the left and down on the right for end behavior. So my roots are at 0 and negative 2. Let's plot those. 0, negative 2. My y-intercept is at y equals 0. It's right here. My end behavior is up on the left and down on the right. The last step is the hardest step. I have to connect those dots in a way that respects what the root multiplicities have to say. And the root multiplicities say, let's cross the axis when x is equal to 0. And let's bounce when x is equal to negative 2. So cross the axis when x is equal to 0 looks like that. And bounce when x equals negative 2 looks like this. And then I connect the dots. And that looks like this. That's not super precise, but it is good enough because it captures the right roots, the right multiplicities, the right y-intercept, and the right end behaviors. And that's all I care about in this class. All right, any questions? All right, please stop me and raise your hand if you've got any questions as we go along. Be happy to answer. Graph the given polynomial function. This time, we get our function in factored form. And that makes it easier. It is easier to graph in factored form. Because a lot of times, the hardest part is finding what the roots are. But if it's already factored, you get the roots easy. The roots are, and their multiplicities are, very good. If it's in factored form, then the y-intercept is a little bit harder to find. The y-intercept is if I plug in x equals 0, and that's going to be 1 over 16 times 0 minus 2 times 0 plus 1 times 0 plus 4 squared. So this is 1 over 16 times negative 2 times 16. Very good. So the y-intercept will be at -2. The last thing I need to know is my end behavior. And the end behavior cares what is my degree. Mhm. How did you know the degree was 4? You add the multiplicities. Again, if you're looking at a polynomial in expanded form, then the degree is the largest power of x. But if you're looking at a polynomial in factored form, you add up the multiplicities to get your degree. So 1 plus 1 plus 2 is 4. 4 is an even degree, and my leading coefficient, is it positive or negative? It's positive. And with an even degree and positive leading coefficient, that tells me my end behavior is up on the left, up on the right. Again, you're supposed to have that little table memorized. I don't remember what page the table was on, but we'll try to find it. Right? Positive leading coefficient, even degree. That's up on the left, up on the right. And you have to memorize that before your next test. Now, I'm totally prepared to graph this thing. The first thing I'm going to do is I'm going to put down 4 dots corresponding to these 3 x-intercepts that I have, and my y-intercept, which is now -2. So 2, -1, -4, 2, -1, -4. Those are my 3 x-intercepts for my 3 roots. And then I have one y-intercept at -2. So I've placed dots for all my x and y intercepts. The next step is I put down my end behavior, and my end behavior was up on the left. So start at the leftmost dot and draw up on the left. Boop. And then start at the rightmost dot we have plotted and we draw up on the right. Whoop. And then the hardest part is I need to connect these 4 dots in a way that truly respects what they want to do according to their multiplicities. And if the multiplicity is odd, this is going to cross. So where I have odd numbered multiplicities, we're going to cross the axis. And if the multiplicity is even, like the number 2, we're going to bounce. So at x equals -4, we bounce. This is what bouncing looks like. Oop. But when x equals +2, we're going to cross the axis. And when x equals -1, we're going to cross the axis, like that.
Does it matter how high you go up?
No. Yeah, that won't matter at all. What I really care about is not how tall these are or where the maximum and minimums are. What I really care about is making sure we get the roots, the y-intercept, the multiplicities, whether it bounces or crosses, and the end behavior. And this is good enough. The way you could check your work if you're doing this problem is with Desmos, right? You go back here and type in 1/16 x minus 2, x plus 1, x plus 4. I think it was x plus 4. Yeah. And then you look at your Desmos graph, and you look at your graph, and you think, well, did I get the right end behavior? Up on the left, up on the right, yeah. Did I get the right roots? -4, 1, -1, 2, yeah. Did I get the right y-intercept at -2? Yeah. Did I get the bounce, cross, cross? Bounce, cross, cross? And it's good enough. It doesn't look exactly the same, but it's, like I said, that's all we want to know. Okay, little pause for questions. Anybody got any questions about what we did? Okay, let me show you a new kind of question, but this is honestly easier. I'm also going to tell you that there is one question like this on your final exam at the end of the semester. So we'll talk about this closer to the end of the semester as well. But the final exam question kind of looks like this. It won't give you a function. It's not going to tell you what the function is, but it will tell you that your polynomial function has roots at -4, -3, and 3, and that those roots have a multiplicity of 2, 2, and 3. It will also tell you that your y-intercept is at -3, or something like that. It will give you a description rather than giving you a function. But you would go to graph this exactly the same way. You say, all right, every one of my roots is a y. No, every one of my roots is an x-intercept. So here's -4, here's -3, and here's +3. I'm also going to put a dot down for my y-intercept. Normally, my next step would be to draw the arrows for the end behavior. Except my little description didn't tell me what the end behavior is. So we're going to skip that for right now. And I'm going to move on and try to connect these 4 dots in a way that's okay with the multiplicities. Starting with this root at +3. Since the multiplicity is odd, this is going to bounce or cross? It's going to cross the axis. Odd multiplicity, so it's going to go through the axis right here. And if I have to start from this y-intercept, let's try to connect this dot to the root over here. And then it's going to cross the axis. And there's no more dots, so the right side end behavior has to go up, right? It can't cross the axis again, so it's got to keep going up. Whenever I try to connect this next dot, I'm going to think, as I'm as I'm connecting that dot, the multiplicity is even, so it's going to bounce. I'm not going to cross the axis here, so let's try it. Connect the dot, but don't cross the axis. And then when I come in to connect this dot, this is even, so it's going to bounce. Once again, I'm going to connect the dot, but I'm not going to cross the axis. So the left side of the behavior has to be down. Hopefully this question is easier because you don't actually have to do any of the work. Figuring out what the roots are, figuring out what the y-intercept is, figuring out the end behavior. You just got to connect dots. You've got to remember this multiplicity rule. Do another one. This will be our last one for today. We want to graph a function that meets this description. It has 3 roots at -2, 0, and 3, and those roots have a multiplicity of 1, 1, and 2. So let's make those dots. -2, 0, and 3. Normally, I would want to know what is my y-intercept. so I could put that dot down. But if you look, I actually already plotted my y-intercept. So that y equals 0. So that's good. I want to write down arrows for my end behavior. And I know my end behavior is up on the right. I just don't know what's happening on the left side. So maybe I draw an arrow that goes up from the rightmost point. And the next step is I just got to connect these dots in a way that works with these multiplicities. And this multiplicity is even, so it bounces. So here, don't cross the axis. This multiplicity is odd, so it crosses. As I connect this dot, I'm going to cross the axis. And then this multiplicity is odd, so I cross the axis again.